What's up guys, my name is Ritvik and today I'm here to teach you everything you need to know about Unit 6 Part 1 from AB Calculus AB and BC. So for AB students, this video has everything you need to know for Unit 6. But for BC students, there's a Part 2 video that you must watch. So now before I begin, please go to the description right now and get my free AB Calculus AB and BC books because those books have everything you need to know to get a 5 and an A in your class. So what are you waiting for? Get it right now. And now let's begin immediately. So an integral represents the area under a curve and is different from a derivative since the derivative was the slope at a specific point. So Riemann sums is basically a useful way that we use to approximate the area under a curve. And then Riemann sums involves adding up either rectangles or trapezoids to find the area under the curve. So basically you will be given the interval to integrate under, and then you also be given the number of rectangles to use. So using that you can find the width of each rectangle or subinterval. So basically, if the interval is from A to B and the number of rectangles used for Riemann sums is n, then that means the width of each rectangle will be b minus a over n. Now let's look at an example. So there's multiple types of Riemann sums. So the first one that I'm going to be telling you about is left-hand Riemann sums. And for a left-hand Riemann sum, it's the left vertex that lies on the curve. The top left vertex lies on the curve. So in this situation, as you can see, for example, look at the orange rectangle. The top left vertex lies on the curve. Now look at the red rectangle. The top left vertex at x equals to 2, that lies on the curve. Now look at the green rectangle. The top left vertex at x equals to 3, that lies on the curve. So the width of each rectangle can be found, again, by dividing the width of the integration by the number of rectangles. So in this situation, we're integrating from 0 to 5, and I want to use 5 subrectangles, right? 5 rectangles. So that means each should have a width of 1. So that means the first one will go from x equals to 0 to x equals to 1. The second one will go from x equals to 1 to x equals to 2. The next one will go from x equals to 2 to x equals to 3. Those are the bases, right? So basically, I will substitute x equals to 0 into the equation to find the height. Then I'll substitute x equals to 1 to find the height for the orange rectangle. And then I'll substitute x equals to 2 into my equation y equals to x squared to find the height. Now this is very important. So now the area is 1 times f of 0 plus 1 times f of 1 plus 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4. And this is all color-coded, so you can go back to match it with the rectangles I just showed you. So I can substitute each of these numbers into y equals to x squared to find these function values. And then after I add each of these up, I can find that the answer is 30. Now I'm going to be teaching you about the right-hand Riemann sum. And the difference is that the top right vertex, that's the one that lies in the curve instead of the top left vertex. So again, we have 5 rectangles, each with a width of 1. So the first one, the base is from x equals to 0 to x equals to 1. The second one, base is from x equals to 1 to x equals to 2. And for the left-hand Riemann sum, we use the left endpoint, right? But for each rectangle, now we're going to be using the right one. So now to find the height for the first rectangle, we'll use the point x equals to 1. Now for the second rectangle, we'll use the point x equals to 2. And for the third rectangle, we'll use the point x equals to 3. So that means the area is 1 times f of 1 plus 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4 plus 1 times f of 5. Now since the equation is y equals to x squared, I can plug in each of these points into my equation. And then I can add all of these terms up to find that the area is 55. Now I'm going to be teaching you about the midpoint Riemann sum. And for a midpoint Riemann sum, the difference is that the midpoint, right, of the rectangle, that's what lies in the curve. So again, we're integrating from 0 to 5, so we're going to be approximating the area under that using the midpoint Riemann sum. So basically, the first rectangle, right, we know that the base of it goes from x equals to 0 to x equals to 1. So now to find the height, we will plug in 0.5, since that's the midpoint. Now for the next rectangle, which has a base from x equals to 1 to x equals to 2, and it's orange, right, I'm going to be using x equals to 1.5 and plugging that into y equals to x squared to find the height. For the next rectangle, the red one, I'll be using 2.5, and for the green one, I'll be using 3.5 for x, and for the last one, I'll be using 4.5, because this is the midpoint Riemann sum. And this means, now that means the area can be represented as 1 times f of 0.5 plus 1 times f of 1.5 plus 1 times f of 2.5 plus 1 times f of 3.5 plus 1 times f of 4.5. So now I can substitute all of these into y equals to x squared. And after that, I can find that the area is 41.25. Now, let's look at the trapezoid Riemann sum. Now for this, both the left and the right endpoint, they both will lie on the curve. So for example, look at the orange trapezoid. As you can see, the point at x equals to 1, that also lies on the curve, and so does x equals to 2. And now that means we have all these trapezoids now. So we can find the area using that. So for each of those trapezoids, we'll average the bases. For example, for the orange trapezoid, one base has a length of f of 1 and the other base has a length of f of 2. So we're going to be averaging that out and then multiplying it to the height, which in this situation, it looks like the width, but it's the height if you turn the trapezoid 90 degrees around. So that means the area is f of 0 over 2 plus f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5 over 2. And you can pause the video and look at how I simplified this. Now I can plug in each of these numbers into y equals to x squared, which is a function, to find that the area is 0 plus 1 plus 4 plus 9 plus 16 plus 25 over 2. And I can add each of these numbers up to find that the total area is 85 over 2. So now remember that if a function is increasing, then Rem, which is the right-hand Riemann sum, it will be an overestimate, while Lrem, which is the left-hand Riemann sum, will be an underestimate. Now, this is the function y equals to f of x, and this represents the Riemann sums, basically the area under the curve, the approximation for it. The more the rectangles, the more accurate the area is. If we have an infinite number of rectangles, it's going to be so accurate. So look at how I'm increasing the number of rectangles. This is making the area more and more accurate. That is what we want. So if the number of rectangles approaches infinity, then our area will be extremely accurate. And this brings us to definite integral notation. So the definite integral notation is the limit as n approaches infinity, which is basically the number of rectangles approaching infinity and the summation from k equals to 1 to n of b minus a over n, which is the width of each rectangle, times f of a plus b minus a over n times k, which is the height. And this is the same thing as the integral of f of x from a to b. Now the fundamental theorem of calculus. Now this is very important. So if we're differentiating with respect to x, the integral from a to x of f of t, then this is the same thing as just saying f of x. However, what if these integration bounds are also functions, right? Such as from h of x to g of x. So what we do is we simply plug in each function into the function f. So I get f of g of x. However, I multiply this to the derivative of g of x minus f of h of x times the derivative of h of x. Now let's look at an example. So d over dx, of the integral from 2 to x squared of sine of t. So what I do is I simply plug in x squared into the sine function to get sine of x squared times the derivative of x squared, which is 2x. So I get 2x times sine of x. Now, if I plug in 2, I get sine of 2. But now when I multiply by the derivative of 2, I get 0. So that means the answer is just 2x times sine of x squared. Now, accumulation functions are super important. You must know how to interpret them. If we know that g of x is basically the integral of the function f from a to x, then we can differentiate both sides to see that g prime of x equals to f of x. And this is important because now if someone asks you, when is g of x increasing? You could say that it's increasing when the first derivative, which is g prime of x, when that's positive. But you can also say that it will be increasing when f of x is positive, because we know that g prime of x is the same function as f of x. Now, properties of definite integrals. The first one says that if the integration bound is from a to a, then the area is 0. And that makes sense because if the width that you're integrating under is 0, then there's no area indeed. And the next one is the integral from a to b, right? If you're integrating from a to b, that's equivalent to the negative of the area from b to a. And this is because we reverse the interval. And now, if we have a constant multiplied to a function and we want to integrate that, we can simply factor the constant out. And the third one says that if we're integrating the sum of two functions, such as f of x plus g of x, then we can split and separately integrate each function. And that works for subtraction also. And then the other rule is the adjacent intervals one. If we're integrating the function f of x from a to c, and then we want to add that to the integral for f of x from c to b. And since if c is in the middle of a and b, we can simply say that the integral is f of x from a to b. So let's look at an example. So the integral of f of x from 2 to 3 is 3, and the integral of f of x from 3 to 5 is 4. And now using this, I want you to find the integral of f of x from 2 to 5. Now, we can notice that this is an adjacent interval because 3 lies between 2 and 5. So that means we can simply sum up each of the two integrals that were given to get 3 plus 4, which is 7. Now, given that the integral of g of x from 2 to 5 is 3, I want you to find the integral of f of x plus g of x from 2 to 5. Now, I can simply split up and separately integrate each term. So I separately integrate f of x from 2 to 5, and then I separately integrate g of x from 2 to 5. So we already found that f of x from 2 to 5, the integral of that is simply 7. and then for g of x, we're given that it's 3. We can add both to get 10. Now an antiderivative and the fundamental theorem of calculus. So basically the antiderivative of the function f of x, if that's uppercase f of x, then that means the derivative of uppercase f of x, that function, is f of x, the lowercase f of x. Please look at the writing that I've written down on the screen. And then if f of x equals to x to the power of n, then that means the antiderivative will be x to the power of n plus 1 over n plus 1, plus c, the integration constant. If f is a continuous function for the interval from a to b, then the area under the curve of f of x for that interval can be represented using the antiderivative. It's simply f of b minus f of a. And this is the fundamental theorem of calculus. So let's look at an example. The integral of 2x from 0 to 2. So we know that the antiderivative of 2x is x squared. So that means we want to find 2 squared minus 0 squared, which is simply 4. Now finding antiderivatives and indefinite integrals. Now these are some key strategies. So basically, convert all radicals to exponential forms. And whenever you have a polynomial in the numerator and a single variable in the denominator, divide both of the expressions. And be careful with terms like e and pi. For example, the integral of e with respect to x will be e times x because e is a constant and so is pi. And don't forget your integration constant. Now let's look at an example. The integral of x cubed divided by x4 times the cube root of x. So I convert my radical to exponential form, and then I can simplify this because I know when I multiply two terms with the same base, the exponents add up. So I get x to the power of 3 divided by x to the power of 13 over 3, which is x to the power of negative 4 over 3. Now the integral of that is simply minus 3 times x to the power of minus 1 over 3 plus c, the integration constant. Now another example is x squared minus 6x plus 3. Now let's integrate x squared minus 6x plus 3 divided by x. So again, I have a single variable in the denominator. It makes sense to use polynomial division, and I get x minus 6 plus 3 over x. And now I can integrate this to get x squared over 2 minus 6x plus 3 times the natural log of x plus c. Now u substitution is extremely important, and this is probably the most important part of this unit. So u substitution, basically you substitute a simple variable like u for a complex expression. However, substituting for u that involves dx in the integral prevents us from integrating. However, we can find a relationship between dx and du and substitute that in also. And to do that, you differentiate the substitution that you make. And u in this substitution should be the inner function of a composite function. Let's look at an example. Now, I want to find the integral of 2x times the cosine of x squared. Left substituting u equals to x squared. Now, if I put in u equals to x squared, I get 2x times the cosine of u, the integral of that. Now that's complicated because we have u and x. However, I can differentiate the substitution u equals to x squared. And if I differentiate that substitution, I get du equals to 2x times dx. And now I can substitute that in to get that my integral is cosine of u du. And the integral of that is simply sine of u. And now I can substitute x squared for u to get sine of x squared plus c, the integration constant. Now another example is the integral of x times the square root of 1 plus x squared. Let's substitute in u equals to 1 plus x squared. And in general, if you have a term with a higher degree than another, substitute u in for that. Because after I differentiate it, I'll get a term that's 1 degree lower. So to substitute u equals to 1 plus x squared, I will differentiate this equation also to get du equals to 2x times dx. Now I can substitute both of these in to get 1 over 2 times the integral of the square root of u. And this is simply 1 over 2 times u to the power of 3 over 2 divided by 3 over 2. And this simplifies to 1 over 3 times u to the power of 3 over 2. Now the main step is that you must substitute in the substitution we made initially. So initially we said that u equals to 1 plus x squared. So we substitute back in to get 1 over 3 times 1 plus x squared to the power of 3 over 2 plus c, the integration constant. Whenever you're finding the definite integral using u substitution, you can leave your answer in terms of u, as long as you integrate with the right integration bound. So there's no point of putting back in the expression that you had in terms of x for u. Instead, you can keep your answer in u. You can integrate with u and du as long as you change your integration bounds. And to do that, you simply plug in the original bounds into the substitution you made for u, and those will be the new bounds. Now integrating with long division. To do this, you simply divide using polynomial division and then you integrate afterwards. Let's look at an example. The integral of 2x cubed plus 3x over x minus 4. Using polynomial division, I get 2x squared plus 8x plus 35 plus 140 over x minus 4. Now I can integrate this to get 2 over 3 times x to the power of 3 plus 4x squared plus 35x plus 140 times the natural log of x minus 4. Now, integrating with completing the square. You complete the square of the denominator, and often, inverse trigonometric identities are used after completing the square. Let's look at an example. The integral of 1 over x squared plus 12x plus 37. I complete the square to get 1 over x plus 6 squared plus 1. And I should notice that this is quite similar to the derivative of the arctan function, which was 1 over x squared plus 1. Let's make the substitution u equals to x plus 6, which means that du equals to dx. And after I do that, I get the integral of 1 over u squared plus 1 with respect to u. And I can integrate this to get arctan of u plus c. Now I substitute in u equals to x plus 6 back in to get the arctan of x plus c plus c. So now let's look at an actual free response question from the actual AP exam. Please pause the video and try the problem on your own. So by now I hope you actually paused the video and tried the problem. So the first part says estimate f prime of 4, which is basically the slope at x equals to 4. So basically I'll use the point closest to 4 to the left and the point closest to it to the right. So I'll use x equals to 3 and x equals to 5. So that means I want f of 5 minus f of 3 divided by 5 minus 3. So I can use the values in the table to get negative 2 minus 4 divided by 2, which is negative 3. Now for part B, we want to estimate this integral, right, from 2 to 13 of 3 minus 5 f prime of x. So I'm going to split the integral up, and I'll separately integrate 3, and then I'll separately integrate 5 times f prime of x. So if I integrate 3 from 2 to 13, I simply get 3 times 13 minus 2, which is the width, which I'm integrating under, which is 33. Now I want to find 5 times the integral of f prime of x from 2 to 13. And using the fundamental theorem of calculus, I know that that integral is f of 13 minus f of 2. So I want to find 5 times f of 13 minus f of 2. And I can use my table to find that this is 5 times 6 minus 1, which is 25. And that means my final answer is 33 minus 25, which is 8. Now for part C, I want to use a left-hand Riemann sum with subintervals indicated in the table, right? To find the approximation, the integral from 2 to 13 of f of x. So in this situation, not all subintervals will have the same width. Just remember that sometimes using the table, it won't have the same width. So basically the first rectangle will be from x equals to 2 to x equals to 3. The second one will be from 3 to 5. The next one will be from 5 to 8. And the last one will be from 8 to 13. And since this is a left-hand Riemann sum, f of 2 will be the height of the first rectangle, f of 3 will be the height of the second one, and then f of 5, and then f of 8. So using left-hand Riemann sum, I can get f of 2 times 3 minus 2 plus f of 3 times 5 minus 3 plus f of 5 times 8 minus 5 plus f of 8 times 13 minus 8. And now using the table, I can find the values of each function, and I can expand this to get 18. Now this is another free response question from the actual AP exam. Please pause the video and try the problem on your own. So by now I hope you actually tried the problem. So now let's see the solution. So for part A, we want to find g of 4 and g of minus 2. So we already know that g of x is the integral of the function f from 1 to x. So g of 4 is the integral of f of t from 1 to 4. So we want to find the area under the curve, and we're already given the graph of f. So we can find the area under the curve by splitting it up into simpler expressions, like what you see on the screen. So I can find the area of each section, and I can add the area up, and I also color-coded it so you can see the area of each. And now I can simplify this to get 5 over 2. And then to find g of minus 2, I can first notice that the area from minus 2 to 1 is simply a right triangle, and that has an area of 4 times 3 over 2, which is 6. However, I want to find the area from 1 to negative 2. So what I found was the area from negative 2 to 1, but I want to find the area from 1 to negative 2. So I can simply reverse the sign to get that the area that I want is minus 6. Now for part B, we want to find the instantaneous rate of change of g with respect to x at x equals to 1. So let's differentiate our function g. So we know that g of x equals to the integral of f of t from 1 to x. So if I differentiate that, I get the g prime of x equals to f of x. Now I substitute in 1 to get g prime of 1 equals to f of 1. And I can look at the graph to find that f of 1 is simply 4. Now for part C, I want to find the absolute minimum value of g for the closed interval from negative 2 to 4. Now to do this, we're going to be looking at critical points to look at what points we need to test. So a critical point will occur when the first derivative of g is 0. And we know that g of x equals to f of x, which means, and we can see that at x equals to 3, f of 3 is 0. So we have a critical point at that point. We need to test. Now we can notice that f of x is greater than 0 for negative 2 to 3, and it's less than 0 for 3 to 4. And that means it increases and then decreases. So we have a relative maximum at that point. So a relative maximum can never be the absolute minimum in this problem. So we can ignore x equals to 3 because we know a relative maximum exists at that point. So now we test the endpoints, negative 2 and 4. Again, whenever you're finding absolute extrema, you must test your endpoints. So now I test my endpoints. I already know g of negative 2 is negative 6. I already found that in part A. And I already found g of 4 in part A. It was 5 over 2. And clearly the minimum of this, the least of it, is minus 6. Now for part D, it says the second derivative of g is not defined at x equals to 1 and x equals to 2. Now we want to find how many of these values, these x coordinates, are points of inflection for the function of g. So a point of inflection occurs when the sign of the second derivative changes. So we already know that g prime of x equals to f of x, which means that g double prime of x is f prime of x. We can notice that at x equals to 1, g double prime of x, which equals to f prime of x, that changes signs. But at x equals to 2, it does not change signs. So that means an inflection point cannot occur at x equals to 2 because the sign of the second derivative does not change, but it indeed can occur at x equals to 1 because the sign changes.